Thanks. Buenas tardes.
All right, it's 1 o'clock. Let's go and get started. All right, good afternoon, everyone. How's everyone doing today? Good, doing good. Weather's better. Still cold, but it's at least it's not drenched out there, so that's good. Okay, so today we're going to continue with our discussion of present worth analysis, and so we're just trudging right along. Remember, homework problem set 1 is due very soon. I do have homework set 2 ready for you guys, but I'm going to wait until the due date for homework 1 is passed before posting it. But that's going to be covering present worth analysis, all the non-standard cash flow conversions. So it's a bit of a step up compared to problem set 1. And so, I think generally, for this class, problem set 1 is not too much of a difficulty. Problem set 2 is definitely a step up from that. So, I think I'm going to give you guys probably about 2 weeks to do it, maybe like a week and a half. So make sure you start it pretty soon. Okay. All right. That's about it. I don't have anything else to say. Any questions I can answer before we get started for today? Okay, all right, so let's go ahead and pick up where we left off then. Okay, so I'm gonna scroll up here for a little bit, because when we left off, when I left you guys on Tuesday, we were in the middle of doing this example. So you don't have to write. I mean, this is just from Tuesday, so this should already be in your notes. But basically, we were introducing this idea of present worth analysis to do what I call kind of economic comparisons. And so, a situation you're going to find yourself in a lot when you're doing budgeting and things for engineering projects or even in your own personal life is you're going to be comparing different options, right? And so this happens all the time. And so the idea here is to use kind of what we've learned in terms of equivalent cash flows, cash flow conversions, to do this analysis in a systematic way. Okay. And so this is the example that I gave you guys. And so an engineering company is considering the purchase of 2 different machines. Okay. Both machines are going to perform the same, and so they're going to fulfill kind of their role the same way. The main difference between them is their cost. Okay. So machine A has an initial cost of $10,000, and it's going to have $3,000 a year of revenue. Okay. You're comparing that to machine B, which has a higher initial cost. So machine B costs $13,500. But it's going to provide you more revenue over time, right? And so what we said was that it'll provide you $3,000 in revenue in the first year, but this is going to ramp up by $500 each year after. Okay. And so if we assume an interest rate of 7%, what we want to do is we want to find out, which is the more economically smart alternative, right? You could either go with machine A or machine B. Okay. All right, so to do this, we had a couple steps. So first thing we wanted to do is we wanted to draw their cash flow diagrams, and so we did that here. Okay, so both machines are going to be used for 5 years, and so machine A, you can see there has that kind of big initial cost of $10,000, and then we have kind of a steady revenue after that. So we have a uniform series of $3,000 in years 1 through 5, right? Whereas machine B, we have the higher initial cost. That's that down arrow of 13,500, and we have a ramping up revenue. So we have 3,000, 3,500, 4,000, so on and so forth. Okay. Okay, so one thing you're gonna have to do in all these problems is that when you're given the cash flows in the problem statement itself, you're gonna have to be able to classify these in terms of what types of cash flows that they are. Okay, so for machine A here, we see that we have a present sum, that's our initial cost of minus 10,000. And we have a uniform series of 3,000 that takes place, each year after that. Okay, so we have two cash flows essentially there. For machine B, we have again a present sum and a uniform series, but we also have this gradient that's going to increase our revenue over time. Okay. All right, and so the last thing we did before we left on Tuesday was we set up their present worth equations. Okay, and so when a problem asks you to compute their present worths, basically you're gonna compute all the cash flows for that option into a present sum. Okay. All right. So for instance, for machine A, you can see here that we have two cash flows here. We have the minus 10,000. The minus 10,000 is already in present sum form, and so we don't have to do any conversions there. So we just have a minus 10,000 there. Okay. Then we have that $3,000 that we need to convert. Okay, so because that $3,000 is in uniform series format. Okay, and so to convert that, we can either use the formulas. So we can use our P to A formula, or excuse me, A to P formula, or we can use the compound interest table, which is what I'm going to show you here. Okay, and then we can set up the same equation for machine B, except the only difference for machine B is that we have this additional P over G factors as well. Okay, and so all of these things that I have in parentheses, this P over A factor, P over A factor, this P over G factor, we're going to look these up in the compound interest table. So that's going to be, once you kind of get used to it, once you kind of, you kind of know where to look, what columns and stuff, the compound interest table is going to be very fast. And so I'm going to show you kind of how to do that just now. Okay. Any questions? So that was just kind of a really quick recap of this problem. Any questions on just the setup or kind of how we got here? Okay. All right. So let's take a look. So let's look in the compound interest table. So, when you're looking at the compound interest tables, the first thing you should always look at is the interest rate. Okay. And so we know that we are looking at the table for 7%. Okay. We need to look at the factor that we're looking for. And so we need a P over A factor and the P over G factor. Okay. And then of course you need the number of time periods as well. Okay. But it starts with the interest rate. Right. All right. So let me go ahead and share my screen, my other screen. Oh, that's not it. That's an error. Okay. So this is the compound interest table. So this is posted for you on Canvas, right? And remember, you want to scroll down to the page with the interest rate that we're looking at, right? So the interest rate can be found in the upper left-hand corner of the tables, right? So this table right here has an interest is for 6%. So we don't want this. We want to go down to 7%. So let's go ahead and keep scrolling down, right? And so we go to the table for 7%, right? So we're on the right place. Next thing we're going to look for is the factors that we want. And so we know that we want the P over A factor and the P over G factor, right? So we're going to be looking in these columns here. Okay. And then for the row, we want to look for the row where n is equal to 5. Okay. All right. So we can kind of highlight these two things. And so our P over A factor in this case is going to be 4.11, and our P over G factor is going to be 7.647. Okay. So in our present worth equations that we just wrote down for our example, we're going to write these numbers in for those in those places. Okay. All right. So let's remember those numbers, and then we'll write that into our equation here. Okay. All right, so let's write in the factor for the P over A, right? So P over A, 7% and 5. We know from the tables that this was 4.100. Okay. You can see down here we have the same factor here, right? P over A, 7% and 5. So that's going to be 4.11. Okay. And then for the P over G factor, this was terrible short-term memory. It's 7.647. Let me just double check that quick. Yeah, 7.6%. If I didn't have a dual monitor display in my office, I would be probably 30% less effective because I forget things, you know, in the short memory a lot. Okay, so now that we have these factors in here, now it's just straight arithmetic, so we can just punch these into a calculator. Okay, so for the present worth of A, we have minus 10,000 plus 3,000 times 4.1, and so we plug all of those factors in, we get 2,359 cents. Okay. We do the same thing for B, okay? And so we plug this into our calculator. We get $2,623.92. Okay. All right, and so for this case, you know, we want to choose the machine here that's going to be more economically, you know, better or give us more money. And so you can see from the present worth analysis that option B or machine B is going to be better in this case. Okay. All right. Any questions on how we kind of finished up that example there? Okay. All right. So that's present worth analysis in a nutshell. And so, you know, the basically all you're doing is you're taking each option, converting it into a present sum, and then you're just comparing it between the different options, see which one gives you the highest one. Okay. Before we move on, I do want to take a look at these results in a little bit more detail. Okay. Because you might be wondering, you know, why do we choose present sums, right? So we've learned all these different types of cash flow, present sums, future sums, uniform series, arithmetic gradient. Why did we choose present sums for this type of analysis? Well, you know, the answer to that is that, you know, there are other types of analysis. We are going to learn them eventually. But present sums is usually a good place to start because it's usually the most tangible, the most easy to understand. Okay, because you know, people kind of understand things in terms of kind of what they can have available, right? And so if you look at these two options, right, they both have a time period of 5 years, right? And so this is an investment. This is a decision that you're going to have to live with for 5 years. Okay, a lot can change in 5 years, and so you know it's for a lot of people, you know, it's hard to kind of you know, project or forecast you know, everything that's going to happen over that time. Okay, so what present worth analysis does is that it kind of distills all that information and gives you you know, the result in terms of money that you would have right now. Okay, and so what this analysis is telling us is that if we were to invest in machine B, right? And so, you know, we would pay this $13,500, and then each year after that, we'd earn this revenue, right? You know, the equivalent thing to do is that instead of kind of waiting the 5 years, right? Someone could just hand you a check for $2,623.92, and that would be what we're saying is that this is equivalent to that. Okay, so all the money that you're going to make from this machine over the next 5 years is equivalent to $2,623.92 today. Okay, and when you put things in terms of, you know, money that they can have today, what it's worth in today's time, that's usually the most tangible thing. So present worth analysis is really useful, at least for visualizing and kind of grasping kind of, you know, these you know, somewhat complicated kind of economic decisions in that sense. Okay. Okay. All right, so let's go ahead and move on. Let's do another example. Okay. So this example, you are working for an elevator company, or you're working for facilities that are in charge of a building. Okay, and this building needs to construct an elevator. Okay, and of course, you know, there are multiple different vendors that you can use to construct this elevator. Okay, I'm not going to write the full text for this problem again, just because it's just kind of a little bit time consuming. So I'm just going to give you kind of the highlights here. Okay, So option A is going to be through a company called Otis. We'll call them Otis Elevators. So they gave you a quote for an elevator that's going to cost $35,000 up front. Okay. You do have to maintain it. So this elevator is going to cost $5,000 a year to maintain. And the nice thing about this company is that they have a recycling program. So at the end of the elevator's life cycle, which they recommend is 5 years, you can sell the parts back to Otis for $10,000. So that $10,000 is going to be a salvage value. Okay. So that's the first option. Another option for elevators is actually Mitsubishi. So Mitsubishi, I don't know if they still do. When I wrote these notes, they did make elevators, but they may have pivoted. But Mitsubishi is another company that offers elevators. So you get a quote from them, and they tell you that their elevator is going to cost $50,000. Okay. You do have to maintain the elevator, but as part of the much higher initial cost, they agree to help cover part of the maintenance. And so what you have to pay out of pocket is $1,000 each year for maintenance. Okay. All right. Mitsubishi doesn't have a recycling program, but you did learn from the Otis rep that you could sell the parts of the Mitsubishi elevator to them, but at a much lower price. And so what Otis tells you that you can sell those parts for $5,000. That's going to be our salvage value. All right, so those are our two options. And so if we assume an interest rate of about 8%, okay, let's do the same thing we did in the last example. So let's draw the cash flow diagrams. And then let's use present worth analysis to determine which is the more economically more efficient elevator to go. All right, so this example, very, very similar to the last example. The only difference here is that, we're not considering any revenue. Because typically, most buildings don't charge you to use their elevators unless it's the Stratosphere in Vegas, then you do have to pay for that. But most elevators don't charge you. And so the only thing we're interested in here is minimizing the cost as much as possible. Okay. Right. It's a small caveat, and at the end of the day, the math that you're going to do is exactly the same, except in this case, you're going to look for the number that's going to be less negative than the other. Okay. Okay. Any questions on the setup for the problem? Okay, all right, so let's go and get started. All right, so let's start with the cash flow diagrams. All right, so in this case, the cash flow diagrams for both options look mostly identical because they both have the same types of cash flows. Just the numbers are kind of tweaked a little bit. Okay. So let's start with the Otis one. Zero, 2, 5. Okay. All right, so first we have our initial cost. And so the initial cost of the Otis elevator is 35,000. Okay. Next, we have the maintenance costs, and so the maintenance costs are $5,000 per year. And then at the end of the 5 years, you can sell it back for the salvage value. So our salvage value in this case is $10,000. Okay. All right, so let's do the same thing for Mitsubishi. All right, so just like the Otis elevator, we have our initial cost. We have a higher initial cost here, so our initial cost is $50,000. Our maintenance cost in this case is just 1,000. Okay. And then we have our salvage value. Salvage value in this case is only 5,000. All right. All right, so from the cash flow diagrams, you can see that in this case we have a fairly simple case. Both cases have just three forms of cash flow. They each have a present sum. They each have a uniform series, and they all have a salvage value that's happening in year 5. Okay, and so in this case, we're going to use our compound interest tables to solve the problem. Okay? All right, so let's compute the present worth of the Otis elevator. Okay. And so let's list out all the cash flows here, and then let's add the appropriate conversion factor as needed. Okay, so we'll start with the initial cost. So the initial cost, the 35,000 is already in present form, so we don't need to convert it. But we do need to make sure we make it negative because it is a cost. Okay. All right, next we have our $5,000 maintenance cost. And so this is a uniform series. Okay. And so to convert a uniform series to a present sum, we need a P over A factor. Okay. Our interest rate in this case is 8%, and the number of times that it repeats is 5. Okay. So it's P over A, 8% and 5. All right, and then we have our salvage value. So our salvage value in this case is 10,000. This salvage value is just one lump sum that occurs in year 5. And so the conversion factor we need in that case is P over F. Okay. But our interest rate and the N is the same as well. So we have 8% and then 5. Okay. All right. So we can look these up in the tables, and of course, if you're more comfortable using the formulas, you can do that here as well. But when we look these up in the tables, what we get for this factor right here. So from the table, we get 3.993. And then this factor here, this P over F 8% 5, this is 0.6806. All right, so let's punch that into a calculator. And so if you calculate that out, this is minus 48,159. All right, so that's our starting point. Okay, remember it's a negative answer here because we don't have any revenue, okay? And so we want to pick the option that has a less negative present worth. Okay. All right, so let's do the same thing for Mitsubishi. And since the cash flows are identical, the conversion factor is going to be the same as well. Okay. All right, so just like the Otis elevator, we have our initial cost. Our initial cost in this case is 50,000, so we have a minus 50,000. Okay. Minus 1,000, P over A, 8%, and 5. Okay. Then to that, we're going to add 5,000, P over F, 8%, and then 5. Okay. That 5,000 being the salvage value that we have. All right. But since these are the exact same conversion factors as above, we can go ahead and just plug that into our equation here. Okay. So for the P over A factor, we're going to plug in 3.993. And then for the P over F factor, we're going to plug in 0.6806. Okay. And so we plug all this in, and what we get is minus 50,590. All right, and so now that we've done these calculations, we can now make a decision on which one is better to get. Okay, it's a lot closer than you would think, right? And so I think the initial numbers for these ones are I kind of set them pretty far apart, but you can see that it's actually somewhat of a difficult decision. But the one that does have slightly lower cost here is the Otis elevator. Okay, we want to choose Otis elevator. Okay. So that is a decision that we're going to make again. Any questions on this example here? Okay. All right. One thing I want to highlight before we move on here is that when you're doing these present worth calculations, right? A lot of times I see people just do the problems up to this point, right? They compute the present worths of each one, and then they kind of just leave it there, right? While it's true that this is the bulk of the work, right? This is the bulk of the of what you have to do in terms of calculations for these problems. Remember, at the end of the day, the reason we're doing these present worths calculations is so that we can make a decision, right? We want to choose one, okay? And so it's not enough to just compute all the present worths. I actually do want you to write down on your homeworks, on your exams, which one that you want to choose. Okay. It's a small thing, and I know it seems extremely petty, but I do take points off on the exams if you don't write this. And so if you just give me all these numbers, all these dollar signs and stuff, like, yeah, that's great, that's all the calculations, but a lot of times when you're forwarding this information to your manager, or you're forwarding it to a budgeting agent in your company or whatever, they don't really want to see the numbers. They want to see just what your decision is. So you're going to use the numbers to justify your decision, but you do have to make a decision at the end. So I do want you guys to write down kind of which option that you're going to take at the end. Okay, so let's go ahead and move on. All right, so the two examples that we just did, are kind of show you the basics of present worth analysis. Okay. One thing that you may have noticed about those two examples is that the number of time periods was the same in between both options. Okay. That was very intentional because if you have a situation where where the product lines are different, that's something that you have to account for in your analysis. Okay. So let's talk about comparisons. Comparisons with different time periods. All right, so let me start by saying that when doing present worth analysis, the number of time periods between the options okay? And most of the time when you read about these in the problems, the way the problem is going to describe it to you is the life of the product or the useful life. Okay. Right. So you're comparing option A, option B, and you're using present worth analysis to compare them. They must have the same product lives in order for us to do that comparison, to be a fair comparison. But that doesn't always happen, right? And so if you're comparing different products, usually they have different specs, they have different specifications. And so one product may last longer than the other. Okay. So when the product lives differ, okay, you can't perform the present worth analysis just on that one life of that product. Okay. So for instance, if you're comparing one product that is designed to last for 4 years, and you're comparing that to another project that is designed to last for 6 years, right? Doing a present worth between the two isn't really a fair comparison because one is going to last longer. That means you're going to have higher maintenance costs, you should have a higher initial cost, so on and so forth. Okay. But that doesn't mean we can't do present worth analysis. We just have to kind of adjust it to make this fit. Okay. So to do present worth, and I'll just call present worth PW analysis. Okay. And so what you need to do in this case is you need to find the least common multiple for their product lives and then perform the analysis using that time period. So pretty simple, right? So you just find the least common multiple and then just do that analysis that way. Okay? But what can happen sometimes is that if you're going to use this least common multiple approach, a lot of times this least common multiple is going to be greater than the life of a certain product, right? Okay. And so if the least common multiple um, is higher, what you need to do at that point is that once a product kind of reaches its end of life, we're gonna basically assume that we're gonna buy a replacement at the same cost, whenever it ends. Okay. And sometimes you have to repeat this several times until you reach that least common multiple for the product cost. Okay. All right. It sounds complicated, but once you actually see an example, it's pretty easy actually. Okay. Any questions on this though before we jump into that example? Okay. All right. So let's take a look at an example, see how this works. Okay. So this example, we're going to be, let's say we work for Southern California Edison. So Southern California Edison is considering the purchase of a new pump. Okay. So this is for maybe their hydropower that they may generate. Okay. So they may need a pump to kind of help with that operation. Okay. So just like before, we have two options here. All right. So we have pump A. All right. So pump A has an initial cost of $7,000. It has a maintenance cost of $500. And then let's say that it has a useful life of 12 years. So pump A is designed to last for 12 years. Okay. Then after that, you can salvage it for 1,200. Okay. So usually with these types of systems, like for the power company, they tend to kind of replace their parts before they run to their end of life, mostly just for safety and reliability reasons and so. And so maybe after the 12 years, the pump is still good, but it's kind of it's not as reliable for power generation, which the entire community depends on. And so usually what happens is that these power companies often sell a lot of their parts after they're done with it, but they're usually still good for a few years after that. So that's what that salvage value represents. Okay. All right. So they're comparing that with another pump with a very creative name, pump B. Okay. So pump B has a initial cost of $5,000. Oh, sorry, I should make so pump A salvage value of $1,200 um, after 12 years. All right, back to pump B. So pump B has an initial cost of $5,000. It has a maintenance cost of $1,000 per year. Okay. Okay, so pump B also has a salvage value. The salvage value for pump B is $1,000, but this is after only 6 years of use. Okay. So once again, we are at this junction here where we need to make a decision on which pump to get. Okay, and we're going to use present worth analysis to help us get there. All right. So for both cases, we want to draw their cash flow diagrams. Okay. And then we're going to use present worth analysis to determine which pump to buy. So once again, this is kind of similar to our most previous example. So, we're not given any revenue numbers for the most part, we're just given their costs. And so we want to pick the one that has a lower overall cost. Okay. Oh, we need the interest rate. I always forget to get the interest rate. The interest rate in this case is 7%. Okay. All right. Any questions on the setup of the problem? Okay. All right. So let's go ahead and get started. So let's go ahead and start with the cash flow diagrams. This one's gonna be much bigger because it's for 12 years. So let's start with pump A. Right. So remember, this case we have different product lots, right? So pump A is designed to last for 12 years. Pump B only lasts for 6. Okay. What we need to do in these cases is we need to find the least common multiple. So the least common multiple between 12 and 6 is luckily 12, right? So if we multiply 6 by 2, 6 times 2 is 12, and so that's the least common multiple between these two. Okay? The least okay. Okay, so there is our 12-year timeline. Okay. So for pump A, we have our initial cost of $7,000. Sorry about that. I think I made a typo. So the annual maintenance for pump A is actually $1,500, not 500. So I missed the one there. We'll correct it in the diagram here. All right, so we have a yearly maintenance here. Okay. So that maintenance is going to take place every year up until the 12th year. And that's going to be $1,500. And so, if you look back up here, I said this was only 500. It's actually 1,500. Okay. That's what I thought. It looked kind of mysterious, but this makes a lot more sense. Okay. All right. So usually the more expensive equipments usually take more money to maintain, right? And so it makes sense that this is higher. All right, and that at the end we have our salvage value, and so our salvage value is 1,200. All right, it's pretty straightforward. So that's pump A. All right, so let's do the same thing for pump B. Okay. So remember, pump B is only designed to last for 12 years. Or 6 years, excuse me. Pump B is only designed to last for 6 years, but we need to do our analysis over a 12-year time period because that's how long pump A is going to last. Okay. And so that what that means is that when the first pump reaches its end of life, which is in year 6, okay. Right. What we're going to do and what we're going to assume is that we are just going to buy another pump here. So we're going to buy another pump at year 6, and then that's going to take us to the end of 12. Okay. Of course, this is a big assumption because, first of all, most companies don't keep a product for 6 years. Okay. 6 years is a very long time. And to assume that you can buy it for the same price as you did initially, is another kind of big assumption. But, we kind of make those assumptions just to kind of make the problem a little bit easier to do. Okay. All right, so let's go ahead and draw the cash flow diagram for this. Okay. Okay, so initially at time period 0, we're going to buy it for $5,000. Okay. Then we're going to use that first pump for 6 years, and so 1, 2, 3, 4, 5, 6. Okay. And the maintenance cost for this one is $1,000. That first pump we're going to salvage, and so we're going to salvage it up here for $1,000. And then from there, to get us to the end of the 12 years, we're just going to buy another pump. And so at year 6, we're going to buy another one for $5,000. Okay. So we're going to add our initial cost there at year 6 once again. And then we have our maintenance costs. That'll take us all the way to the end. And then we have a salvage value again at the end of year 12. Okay. All right, so that's how you deal with these problems, right? So you find the least common multiple, and then you just extend the timeline until you reach that least common multiple, buying replacements as you go along. Okay. All right, any questions on this? Okay. All right, so those are the cash flow diagrams. Let's go ahead and do our present worth calculations. Okay, so let's do present worth of pump A first. Okay. This one's a little bit more straightforward. All right, so we have our $7,000 initial cost. We have our $1,500 maintenance. Okay. So since that maintenance is a recurring cost, we need to convert it to a present sum. So we're going to do P over A. Our interest rate in this case is 7%. It's going to take place over 12 years. Okay. So it's minus 1,500 P over A, 7%, 12. And then we have our salvage value, which is 1,200. Okay. That 1,200 is a lump sum, so that's going to be P over F, 7%. And that's also again going to take place in the 12th year. Okay. All right. So just like we did in the last example, we're going to look these up in the tables. Okay. And so if we look this up in the compound interest table, this gives us a value of 7.943. Okay. And then our second value here, the P over F, we're gonna once again look it up in the compound interest tables, is 0.444. All right. And so the present worth of pump A, we just punch that into a calculator, we get minus $18,381.70. All right, so let's do the same thing for B. Okay, so we're going to write out our present worth expression. First thing we have is our initial cost. So we have a minus $5,000. And so that is already in present sum, so we don't need to convert that. Okay. Next, we have our maintenance. And so even though we had to buy another one, right? Because there was no gap in between them, our maintenance here is pretty much uniform all throughout. Okay. So we have our uniform maintenance cost of $1,000 for the entire 12 years. Okay. This is P over A, 7%. And 12. And my iPad's lagging a little bit, bear with it. Okay. Come on. There you go. There you go. Okay. It's like a ghost is running this. Okay. So present worth of B, we have a minus 5,000, minus 1,000 P over A, 7%, 12. That is our maintenance cost. That's occurring every year. Okay. We have to factor in the replacement now. Okay. And so the replacement, we replaced the pump in year 6, right? And so two things happened with the replacement. We salvaged the original pump for $1,000 and we bought a new pump for $5,000. Okay. And so both of those are single sums that occur in year 6. Okay. So let's do the salvage value first. Okay. So the salvage value is a plus 1,000 P over F, 7%, and 6. Okay. So this right here is from the salvage of the first pump. Okay. Next, we need to buy our second pump. And so our second pump is going to be bought again for $5,000. So we have minus 5,000. But this is occurring in year 6. And so we need to convert this back to present day. So we have minus P over F, 7%, and 6. Okay. All right, so this next factor here is the purchase of the second pump. Okay. All right, and then once that second pump reaches its end of life, then we salvage it. Right, so we have another plus 1,000 P over F, 7%. Okay, that second pump we're salvaging in year 12, and so we make that that change to the end there. All right. So our expression is a little bit longer here just because we had to buy the replacement. But now we're at a stage where we can just plug in the values from the compound interest table. Okay. All right. So once again, this value here, we had this value from pump A. We know this one is 7.943. Okay. This value here, this P over F, 7%, 6. This one is 0.6663. Okay. This one here is exactly the same, 0.6663. Okay. And then our final salvage value, this has the same as the top one, the 0.444. All right, so we plug all that in. Okay. So generally what people think when they see the situation is that, most people would actually opt for pump A, right? It just seems a lot less hassle. You only have to buy the pump once. It's going to last for 12 years. You don't have to think about it, right? And so it's less to do. Okay. Because if you buy this pump, it only lasts for 6 years. You have to replace it. That means taking the other one offline, right? It's going to incur, $5,000 again in year 6, right? So, just intuitively, a lot of people would prefer to go with pump A. Okay. But when you actually run the numbers for this, you actually get the present worth for pump B is minus $15,164.20. So even though pump B requires you to buy a replacement in year 6, it's actually over $3,000 more economically efficient, right? It has $3,000 less of present day costs that you can use for other stuff. Okay. Granted, this does depend on a lot of assumptions. This assumes that pump B is going to have the exact same specifications and the exact same price in 6 years, which is, honestly, in this world, kind of very unlikely. But maybe you can cut a deal with the manufacturer. Maybe you can buy two and then just put one in storage and then save yourself some money now. Okay. All right. Any questions on this? Okay. All right. So that's how you do analysis with different time periods. Okay. All right. So you may come across this issue when you're doing your assignments. Okay. All right. So least common multiple trick works pretty well when the least common multiple is fairly convenient. And so this past example, I would say it's fairly convenient. Okay? But what happens if you have a situation where the least common multiple is not convenient, and so it's something ridiculous? Okay. So let's pick two fairly large prime numbers. So that's usually a good way to do this. Okay. So what if you had product A lasts 7 years. Okay. And then product B lasts 13 years. Okay. Two nice prime numbers. Okay. Right. And so when you have something like this, you try to find the least common multiple. The least common multiple in this case is unfortunately just their product, right? So there's nothing else, there's nothing lower that they have in common. Okay. So the product of 7 times 13 is 91 years. Okay. And so if you were to do present worth analysis in kind of the most traditional way, the way that we've been doing today, you'd have to extend their lives for 91 years. Okay. That means you have to buy product A 13 times and you have to buy product B 7 times. Okay. And so at that point, it gets a little bit ridiculous because you're 91 years is a really, 7 years and 13 years is already a very long time, but 91 years is an even longer time, right? With the way things are, there may not even be atmosphere on this earth in 91 years, right? So to assume that we're going to be using the same product for 91 years is not practical. Okay. And so in these kinds of situations, it's okay to kind of cut off the analysis early. And essentially what that means is that you're going to be salvaging, or you're going to be, getting rid of a piece of equipment before its end of life. Okay. Right. So let's say in this situation, with product A being 7 years, product B being 13, maybe we do the analysis for 20 years, right? So, something that's kind of in between the two. Okay. And so if you're salvaging a product before its end of life, most of the time your salvage value is going to increase, right? Think of it like selling a car, right? And so, if you use a car for 5 years versus you use a car for 10 years, right? If you sell it after 5 years, you're going to be able to get more money back because, you haven't used up the car all the way, right? So how do you find that salvage value? Usually that's given to you in the problem. Well, and for this class, that's usually given to you in the problem. In real life, you're gonna have to do, find a buyer, do an analysis and all that stuff. But just for this class, just for simplicity's sake, most of the time it's going to be given to you. Okay? And usually it's written in terms of this. Okay. And so let's say that, some product, so we'll say product A has a useful life of, let's say, 10 years. Okay. So you can use the product for, safely for 10 years. Okay. So if salvaged, right? So if you get rid of that product, so let's say you get rid of it in 5 years or less. If you salvage it within 5 years or less, the salvage value will be given to you as X. Okay. Okay. This is just a made up example, so I don't have numbers for you. Okay. But if you salvage it, if you use it for more than 5 years, so if you salvage it after 5 years, then the salvage value will go down. Okay. We'll just call it Y. Okay. And usually X is greater than Y. Okay. So companies know this, right? And so, companies are always very, they know a lot about kind of the assets and resources that they use. And so, knowing this, a lot of companies will try to get rid of or kind of use a product up to a certain point and then try to sell it off, before its value drops significantly. Okay. And so that's going to be a subject for later on in this semester. So in about 3 or 4 weeks, we're going to talk about asset depreciation and what that means for, saving costs for the company, and more importantly, what that means for taxes. Okay. So it's always something good to keep in mind. And a lot of times, the better option would be to salvage a product or salvage a piece of equipment way before it reaches its end of life. Okay. Just so that you kind of get the most for your return, especially if you're planning on upgrading a system or something like that. Okay. So just another kind of factor to keep in mind when you're doing this types of analysis. Okay. All right. Any questions on that? Okay. All right. So one last topic that I want to go over before we leave present work analysis. I don't know if I'm going to get through all of it just because there is an example I want to do, but it's kind of the last thing we do before we move on to the next thing. Okay. It's this idea of something called a capitalized cost. Okay. And this is a type of problem where you're dealing with an infinite analysis period. Okay. All right, so just like the name implies, sometimes you deal with certain types of projects or certain types of financials that are assumed to have really no end in sight. Okay. Okay. So a lot of examples of this being, like the signs on the road, the roads themselves, right? The sidewalks, right? And so, as long as there's humans on this earth, we're going to assume that there's going to be roads until someone comes up with teleportation or flying cars or whatever. But for the most part, there a lot of these types of, usually the public works types projects are going to be assumed to be maintained indefinitely. Okay. And so, a lot of times these types of projects, they need regular maintenance. If you ask me, I think the 57 freeway has had more than regular maintenance. I think they need to be done with that so I can, drive to work faster. But those projects are expected to incur costs forever, basically. Okay. And so, in these types of situations, the question always comes up, how do we fund these? How do we kind of keep coming up with money, to perform these types of projects? Okay. Okay. All right. And so usually when you have these types of projects, we think of them in terms of their regular maintenance costs. So how much do they need on a yearly basis, on a monthly basis, to maintain their use? Okay. So how much do they need to, how much is it going to cost to maintain them on a regular basis? Okay. All right, so a good thought exercise. It doesn't always end up like this in practice, especially nowadays. It's harder to do this. But a good thought exercise is to think about something called a capitalized cost. Okay? And the idea behind a capitalized cost has to do with our idea of interest and investments. Okay. And so, when you put money into a bank account, right, and the bank account has a certain interest rate, that money it basically generates money on itself based purely on the interest rate, okay? So capitalized cost kind of takes this idea and applies it to these types of infinite horizon projects, okay? So capitalized cost is the amount of money that would be needed to set aside right now at a certain interest rate to yield a uniform cash flow indefinitely. Okay. And so for these types of, public works projects, roads projects, right? That require regular maintenance costs. If you wanted to fund that forever, just based purely on your dividends, based purely on interest rates, the capitalized cost is how much you would need to do that. Okay. Okay. So basically, what this means is that you're going to set aside a very large sum of money. Usually it's very, very large. And then you're just going to collect the interest each year to pay for these maintenance costs. Okay. All right. And so the formula for this is very simple, right? And so let's say that you're setting aside a very large amount P, right? So remember, P is our symbol for a present sum, okay? To compute the amount of interest that you earn from that investment, you just multiply it by the interest rate, okay? This right here is your interest rate. Okay. Of course, the interest rate is in decimal form. And then we have P here, which is our initial investment. Right? We talked about this on, I think, the second day of class in that first week. Okay. And so if you take this product, you multiply the interest rate by the initial investment, this tells you how much interest you're going to generate that year. Okay. All right. If you set up an account like this and every year you withdraw that amount of interest, right? This amount right here, right? If withdrawn, okay? If withdrawn every year, then this becomes basically a uniform series of payments. Right? Because that's money that you're earning on a regular basis, okay? It's just that, we have a formula to compute that, okay? And so the formula for capitalized cost is quite simple. So if we take I multiplied by P, okay? This is going to be equal to a uniform series A, okay? Where this A, may represent, the maintenance costs or whatever, okay? Right? That's how much money you would need on a regular basis in order to maintain your project, okay? And oftentimes, you know, we know what that maintenance cost is. That's just how much it costs to maintain your project. What we're interested in is actually computing P, okay? And so to compute P, where now this P takes the form of the capitalized costs. Okay. All we gotta do is just divide both sides by I. So the capitalized cost P is equal to the yearly maintenance costs divided by I. Any questions on this? Okay. All right. So when we come back on Tuesday, I'll do just a quick example with that. Then we'll wrap up everything with present worth analysis, and then we'll move on to the next topic, which is annual cash flow now. Okay. All right. So remember to turn in homework 1. That one is due very soon. I think a lot of people have already turned it in, so that's good. But make sure you get it in before the deadline. So thank you guys for coming today. I hope you guys enjoy the rest of your day. Hope you guys enjoy your weekend, and I will see you on Tuesday. Thanks, Kartik. Thanks, Ryden.
He's like, what, 5?
Hey guys, have a good weekend. You too.
I have a question.
Sure.
Not for this, well, actually, I do it for the homework for, you know, number 3.
Yeah.
Where it just has like, you know how you put like the answers in, but you want to see like the work, do you just want the equation? And like, how you solve it?
Yeah.
Do you want like the other part where it was like a little table where it's like?
Oh, no. So I mean, for homework 1, there's not that much work
Yeah,
to it because
okay.
it's usually just one equation. That's gonna be more applied for the other ones. So for this one, as long as you have the equation, that's enough work. All right.
And for like classes, I was curious for when you, like, you know how some classes have to correct for a lab or whatever, like the lab is part for it.
Yeah.
But what if you drop like a lecture later in the semester, but you're enrolled in the lab? Are you still able to pass the lab or do they both get dropped?
They both get dropped because if you try to drop the lecture, it's gonna say that you dropped the lab.
I was just curious about that.
Have a good one.
You too.